Hello, everybody. I hope things are going well for you. And this is the video for section 5.3 in Calculus 3. So section 5.3 is about double integrals, but with a little twist. Okay, so speaking of twists, you can see a little twisted object behind me, but this describes something sort of round if you look at it from the top. And that's what this section is about. So this section, well, in the last couple of sections, you learned how to take double integrals. Well, this time in section 3, we are going to study double integrals in polar coordinates. Yes, theta and r. All right, so let's get to it. I promise it's not going to be difficult. It's not nearly as difficult as you may think. All right, so with that, let's go and study polar double integrals. All right, double integrals in polar coordinates. You guys remember what polar coordinates are? You have your basic rectangular coordinate system, right? And this is the one that was invented by Descartes, and it's now named the Cartesian coordinate system after Descartes. And so that's XY, right? And so this is called the Cartesian. I don't know what happened to DES in front of his name, but it's called Cartesian, as Cartes, or more properly pronounced as Descartes. And sometimes it's called rectangular because you see that rectangle right there, right? You could also describe a point, the same point, using this angle theta and this length r, right? And so this is, so here, the point is denoted with xy. These are the rectangular or Cartesian coordinates. Here, it's r theta. I would have preferred theta r, but they didn't ask me. So it's r theta, and this is called polar coordinates, right? And so you should know, basically, you know, the standard conversion, like r is the square root of x squared plus y squared, right? Theta, well, it's hard to describe theta because theta could be, it's not unique, right? X and y are definitely unique. R and theta are not as unique. So you can say tangent of theta is y over x, but even that doesn't do justice because x could be 0 and then this is undefined, right? X is r cosine theta. Where did that come from? Well, that just comes from, you know, trigonometry, right? So that, and then y is of course r sine theta. All right, so these are the things that you should already know, sort of a background. All right, so in terms of integrals, you know, you always take a smaller portion of these pieces, the smaller pieces of the coordinate system. So here we have dx and we have dy. So dA, so remember this is just a tiny piece of a rectangular region, R, and so this dA was dy dx. We also used dx dy, right? So the first and most important part of this lecture is what's the corresponding representation for dA, okay? So dA represents a tiny piece, depending on which coordinate system you're using, right? So we can call this d theta, right? Because that's the angle. And, you know, because here's theta 1 and here's theta 2, and here's radius 1 and radius 2. And that difference we can denote as dr. So the question is, can we just use dr d theta for this? And the answer turns out to be no, we actually have to do something, right? And this is, by the way, a very important thing, okay? Just because it worked in a rectangular coordinate system, it does not mean that it's going to work in the polar coordinate system. So in the next couple of minutes, we will answer this question. It's not the area, the small area of this little region is not dr d theta. It's not. Then what is it? Okay, so in order to answer that question, and I will demonstrate exactly how to find this, and you will forever remember, hopefully, what that dA is in polar coordinates. All right, so I'm going to draw a little picture, a couple of pictures, and then try to explain that to you. Okay, so what's the area of a circle? of radius r? You say, duh, okay, we know the area. The area is pi times r square. Okay, good. What happens if you take a portion of this, like a piece of pizza, a pie, or a pizza or something, right? So here we can denote this as delta theta, all right? And since we are still talking about the discrete case, it's delta theta. Eventually, we can call this d theta if you try to make this smaller and smaller. All right. So if the radius is r, all right. So what's the area of this? The area of this, and by the way, this object is called a sector, not section. The sector is a part of a circle bounded by the circumference and two of the radii. All right. So sector. Right, so this is not too hard to figure out, right? Because, I mean, after all, the area is pi r square. That's the entire circle. But out of this, see, if this is 90 degrees, you just take 1/4 of that. If this is 60 degrees, you take 1/6 of the entire circle, right? So all you are doing is getting the proportion that refers to this out of the 360-degree angle, which we write as 2 pi, right? So then this and this cancels. So this is simply 1/2 delta theta times r square. Oh, I guess I should say r square over 2 times delta theta. Not to be confused with some fraternity called delta theta. But that's the a simple equation for the area of a sector. All right. Now what we have to calculate is the area of a place like this one here, this little piece. Okay. So let's call the smaller radius R1, the larger radius R2. The difference between these is delta R, okay? We have already established this is delta theta, right? And then the question is, what's the area of this, this region that is bounded by two sectors, right? So the big sector, you can find the area using this formula, and then you can subtract from that the area of the smaller sector, right? This is just like your old geometry class from years ago. All right, so, well, the big sector has R2 square over 2 delta theta. That's the area based on this equation. The smaller circle, of course, is similar, R1 square over 2 times delta theta. And this, of course, you can take out delta theta over 2, you can factor this out, and then basically what you have is R2 square minus R1 square. All right, watch what happens. Our algebra tells us something wonderful, right? Because you have the difference of two squares. This is simply R2 plus R1 times R2 minus R1, okay, right? So that's nice. Now this, eventually what we want to do is to make this really, really small. So we want to let so let's go ahead and write it here. Let delta theta approach 0 and let R1 and R2 approach the same radius. So I'm going to let R1 get closer and closer to R2, right? So in that case, let's call this R, okay? In other words, we're trying to make both of these numbers closer and closer to some fixed radius R, okay? I mean, that's what we do in calculus. We try to make things infinitesimally small, and that was the whole idea of that integral, that we went from the partitions, and then we try to refine partitions until the norm of the partition goes to 0. So if this becomes the same radius R, okay, this becomes 2R. Okay, and then this, of course, becomes closer and closer to, well, this is what we were talking about. This is the delta R, right? And so that is what? Okay, so you have delta, let's erase this one here, delta theta over 2, and then 2R, and then you have delta R. Okay, the difference between R2 and R1 is getting smaller and smaller, but that area, that difference is delta R. Okay, 2 and 2 cancel. All right, so here is what we see here. Therefore, okay, you ready for this? The small region, when you make these things approach 0 and you take the limit, what you get is the area of the small piece. bounded by two sectors, and that dA is the area. We can use dA to denote the area. That dA is, and remember, this becomes delta theta, d theta. This becomes dr, and the only thing you have left is this thing here. Where did that come from? It came from here, okay, divided by 2. So the answer is r dr d theta. So you have 3 things multiplied together, right? Now, originally I asked you if dA is just just like in Cartesian coordinate system, is dA simply dy dx or dx dy? And the answer is no, it's not dr d theta or d theta dr. So the question, what then is it? The answer is right here, okay? dA, that differential in polar coordinates is going to be not just dr d theta, but add r to it. R dr d theta. All right, now hold on just a second. Why is it, does it make sense to have r in there? I think it does, right? Imagine dr here is the same. Okay, now this little strip here and this little strip here, which one looks bigger? Of course, this one looks bigger, right? Because it's farther and you have more this way, right? So it makes sense that the area is proportional to r, because the farther you go, the bigger this area becomes, even for the same thickness of r and for the same the theta value. All right, so this is bigger, and if r is twice as big here, then this area will be twice as big. So that's what this is saying. It is very consistent with what we know intuitively. Okay, so with that, let's go ahead and try to do some problems here. Now, in order to set up and solve polar double integrals, you need to be able to describe some regions in polar coordinates, all right? So for instance, if you have a, well, let's say you have a circle of radius 1, okay? So this region can be described as r, let's see, r is between 0 and 1, and theta is between 0 and 2 pi, right? Okay, no problem here. How about a region like this? Can you try to describe this? Okay, so this will be R1. Now, how do you describe R1? Well, you can say theta goes from 0 to pi over 2, and R goes from 0 to 4. Okay, so that's no problem there, right? So what you have to do is to use theta and r to describe a region. Now this, so this is using polar. Okay, can you describe R1 using rectangular coordinate system? You could, you really could, okay? If you really wanted to use, I hope you don't, but if you really wanted to use a rectangular coordinate system, x is between 0 and 4, okay? And for each x, I use the blue here, right? Y goes from 0 to this point. Now this point, remember, this is x squared plus y squared is equal to 16. Solving this for x, you get y goes from 0 to, and this is the upper half, so it's the positive square root of 16 minus x squared. And so this is what you will have to do if you used rectangular coordinate system, okay? I say this is easier, and this is much simpler. So whenever your region is a circle or part of the circle, or it has something to do with the circle, all right, then what you want to do is to use polar integrals as opposed to rectangular integrals. All right, so let's do an example. It's a classic example where we know the answer first, right? Let's integrate 1 f of x, y. Let's use r theta now, right? Because we are in polar coordinates. And so what happens when you integrate 1? Okay, so what I want to tell you is this. Let's say r1. Yeah, let's use this r1 here. Now, if you, here's your r1. Okay, it's a quarter of a circle of radius 4. And if you take the integral of 1 over r1, okay, so that's dA, right? Do you remember what this stands for? Do you remember that this represents the area of the circle, right? You can think of this as the height 1. You remember we talked about if you have a quarter circle here, basically you're trying to integrate a solid whose thickness is 1 over this region R1. That's one way to think about this. That's the 1 inch thick steak I was referring to. That's one thing. The volume of that is certainly this, but it's also the area, right? Because when you integrate just 1, you just get the double integral of dA over the region. And by definition, that is the area of the circle. So you know the area of the circle. The area is 1/4 times pi r squared, right? Pi r squared being, of course, that. And so this is 16 pi divided by 4. 4 pi should be the answer, all right? What I'm saying is the area of this quarter circle is 4 pi. We know that, right? Let's verify that using this double integral. How does it work? Okay, remember I said theta goes from 0 to pi over 2. And r goes from 0 to 4. And then you have 1, and then what? You substitute dA, but remember dA is not just dr d theta. It is r dr d theta. Where did that r come from? It's right here, okay? So every time you do double or even triple integral in polar coordinates, you are going to see that r before dr and d theta. And just for your information, you hardly ever switch the order of this. Okay? I know that sometimes dx dy became dx, dy dx, and so on. But with respect to the polar coordinates, this order is almost always dr d theta. Okay, so this is simple because what's r? Well, r becomes r over 2, right? And then you go from 0 to 4. And then d theta, I am just doing this part right now. And so this is 4 times 4 divided by 2, and that is 8. And then, of course, you have pi over 2 multiplying by that, and that's 8 pi over 2, that's 4 pi. And that's exactly what you wanted to see, and so that is how you do that. All right, so that's no problem here. Now, I want you to try to set this up in rectangular coordinate system. All right, I want you to write a double integral that represents the area of R1 using rectangular coordinate system. All right, and you can do dy dx since that's you can consider this as region, the type 1 region. All right, and so when you go ahead, you don't have to solve this because the answer will be 4 pi. But when you set up the integral, then you can come back and go to the second part of this section.